So this is just an example with the vinyl chloride example. As you can see, we're going to use vinyl chloride as the semester-long example. So here you need to satisfy the capacity, which is 800 million pounds of per year of vinyl chloride monomer. The following possible alternatives are gathered from the scope of work. So I have access to the scope of work. They tell us that potentially we can get a competitor's plant which produces this amount of the vinyl chloride monomer and is located about 100 miles away. That might be expanded to produce the required amount that we need. So that's an alternative for us to produce and meet the demand that the scope of work has. This can be shipped to our plant. In this case, the design team projects the purchase price and design storage facility. So in this type of alternative, this solution do not require that you create a chemical plant. You're basically outsourcing the production of the vinyl chloride, but it's potentially feasible, right? It's an alternative that you can take. The second alternative is to purchase and ship by pipeline from a nearby plant chlorine from the electrolysis of sodium chloride. So you have now this resource available, the chlorine. React the chlorine with ethylene to produce the monomer and HCl as a byproduct. So now we are having an idea of what type of reactant we can purchase and what we have available nearby. Alternative 3, since the existing company produces HCl as a byproduct, we have that already in the plant. In large quantity are produced. HCl is normally available at low prices. Reaction of HCl with acetylene or ethylene and oxygen could produce this product and an intermediate that can be cracked to produce vinyl chloride. So now you're exploring a different type of alternative. Notice that the first one do not require that you do any process design development, but the second and the third they do, and they are different, right? The level of complexity, the first one has a direct reaction to produce the monomer. The third alternative have 2 steps, right, to produce the monomer, but they're completely viable. So at this stage, right, we're trying to identify the process for to convert raw materials into the desired chemicals. There's some overall considerations that you need to have in mind. We need to decide the mode of operation. We have batch versus continuous, semi-continuous processes. You may find information in the literature for batch or continuous or semi-continuous. Add them to your research list. Do not discard. However, it is a con, right, if we cannot convert a batch process into continue or a semi-continuous process into continuous, because the only thing that we can simulate are continuous processes in HYSYS. That's one constraint that we have. We need to identify what are the inputs and outputs, not only the overall reactants and products, but intermediate units too. We need to consider the reactors and recycles. The reactors, again, not only we need the process condition, catalyst, conversion, selectivity, any information that you can get about the kinetics, but also you need to find, in terms of the conversion, if you have a low conversion, you have to consider adding recycles in the process to maximize the use of the raw materials that probably are really expensive. And then you need to consider separations and heat integration later in the process. And for the last piece of the puzzle, right, we always need to consider safety and environmental risk and mitigation. So we're constantly doing safety and environmental checks across the different checkpoints in the semester. So what resources we have available? We have the American Nonprofit Scientific Research Institute design reports. They are available. Some of them are available online, so you can look for that. You have encyclopedias available. You have handbooks and reference books. Some of them are online. And in your project resource page, you will have access to our library. And it is a website on our UF library that is dedicated only to chemical engineering books, which I think is really cool. Check the handbooks of chemistries and physics, chemical engineering handbooks, property of gases and liquids, data for process design and engineering practice. In terms of the physical-chemical properties, information that you may need later are the Antoine coefficients. So make sure that you get those too if they are available. Other resources include simulation software databases like Aspen Plus, and we're going to have access to that. Vapor liquid equilibrium data collections. There's some websites online that allows you to download X, Y data sets that you can later use to validate your activity coefficients in the separation part. Journal articles, patents, and internet, right? Patents are super, super useful, and journal articles are too. Make sure that you find them all and you use them wisely. The other thing is I added into the project resource page information on how to cite all of these references. You need to make sure that you use the right format. We're going to stick right now to the IEEE formatting for citations. That means if you're writing a report, you need to use the bracket format every time that you're using the reference. And then at the end, you're going to have all of your references listed in the right IEEE format. On the project information resource page, you will also have information about Zotero. Zotero is a free software that you can add to Word. And what it does, it organizes the references for you in a very neat and the right format already. So I also posted a guideline on how to use that. Zotero is free. EndNote, you have to pay. EndNote is another software that is similar. Either of the two is perfectly fine. If you don't have access to EndNote, you can use Zotero that is free. And I'm using Zotero as part of my research, so it's completely free and it works perfectly fine. There's also environmental and safety data available. Check out for EPA, especially the toxic chemical release inventory, especially when you need to decide if the stream has waste, and this is part of the regulations that you need to consider in the process. Food Drug Administration, journal articles, National Fire Protection Agency, data for process design and engineering practice. This is by Woods, is the author. And of course, the Paris, which is our chemical engineering handbook. Chemical prices are important at this stage. As you are collecting information about your raw materials, make sure that you find their prices. Keep track of the references, and the more citations of prices you have, the better, because you can get a geometrical average to calculate the final prices that you may use for your raw material. These are examples for the vinyl chloride process. Before I move on to go into the concept generation phase, I want to list all the potential reactions that I can find in the literature. So right now my example is with 5 reactions. So I went to the literature, I found that the different patents and articles that describe the reaction, and then I kind of summarized them. And important information are process conditions, if you have a catalyst, if the reactor is defined in terms of the space velocity, kinetics, conversion, selectivity, anything. The more the information, the better to actually understand the process. The other thing that you need to think about of each of them is if are producing toxic chemicals. So you have to go to the MSDS and classify all your chemicals, reactants, intermediates, and products. So those are important consideration when we're going to be narrowing it down, right? These are the constraints of the process. We have to design a process that is safe, not only profitable, but is safe. Once you identify also the reactant products and intermediates, make sure that you get the prices of the reactants and the products, right? Especially byproducts if you don't know the prices of your final product. So you should be doing this in the upcoming weeks. This is an example of very simple preliminary database, but you want to keep track of the different chemicals, molecular weights, chemical formula. If you have the chemical structure, that will be also good, so you can have a visual representation of what it is. This allows you to see if you have things that are miscible, immiscible, so it helps you to understand those physical properties based on the structure of chemicals. I recommend you to use an Excel file because you can classify in the sheets in the workbook on an Excel file. You can say reaction pathway 1, 2, 3, 4, 5, and all of these sheets contains the repository of information, because at this stage, you really don't know what reaction is the one that is going to win. So you just need to collect as much information so you can decide between all of the 8 to 10 that you're going to be collecting. You need to decide which one are the best, are the most promising from that research that you're doing. Organization, I think, is one of the best advice that I can give you at this point. This is the IEEE reference style. You have this available on your deliverable. Notice here I'm putting like a table with all the potential things that you can find in the literature and how they should look like. If you use Zotero allows you to select the formatting, and all of your references will be in the correct format. So that's why it's so useful to use. I believe also Zotero can be added to Google Docs. So you need to check out. I typically use it on my actual work on my desktop, but I believe you can add it as an add-on to your Google Docs. And like that, you can work together and in a collaborative mode this semester. So finally, right, this is the upcoming milestones for the next week. or so. You need to draft an introduction kind of, and the introduction, when I'm saying an introduction, is the introduction to the final report. So you're building right now what is going to become the introduction to your final report. So make sure that you do that introduction, that you do a literature review as part of that introduction. And when I say literature review, do not limit to the reaction pathway. I'm saying the uses, information about safety, information, any type of information about prices, you must add it there, right? And you should also summarize the importance of those references and why they caught your attention, right? And why you're using them. Preliminary database is something that you will be created as you add more information about the reaction pathways. So you need to at least get 10 reaction pathways for your project. And these are just reaction schemes. It could be one single step, multi-step. If you have a reaction scheme, make sure that you pay attention not only to the main reaction, but also to any side reaction that may happen at those conditions. Sometimes that information is not available there. You need to go to another reference and find it out. Reaction conditions, conversion, selectivity, byproducts. Consider reactions with the same stoichiometric, but different catalysts as different reactions. You must include all of the reference that you use. Do not discard anything at this stage. Even that is a batch process, we're trying to be simulating continuous process, but if it's a batch process, just put it there because you never know what ideas you can get later, maybe on the separations or something like that. Also, start building a more robust table with the physical-chemical properties of components involving the reactions, MSDS link, safety and toxicity data, prices for all components. I'm actually asking you as part of this video series to go and select at least 2 reaction pathways that can potentially be used in your project. And like that, if everybody in the team picks 2 reactions, they build their own preliminary database. They find the prices, they find all the information for those 2 reactions. At the end, you will have a very robust report with all of the reaction pathways and the contributions of all of the team members. So with this, I'm concluding this part of the class.